Okay, so I uploaded a document that has a couple of example problems on it. You all can print out and work along with me. These might be in lieu of the discussion problems that we would do on Thursday. I will make a video for each example so you can watch one problem at a time. So this set is going to be finding internal forces and moments at C. So when we start a problem and we need to find internal forces, we need to remember always positive beam notation. And whoops, I can't spell. You may want to put this at the top of your page so that you remember what is positive from which direction that you're looking. And we have to use positive beam notation because, let me try to clear this up right here, because this is talking about behavior. And again, a positive moment tells us that we are creating a curvature. I don't know if you can see, kind of like this, so it'll look like a smiley face. And if we have positive normal force, that tells us that we're in tension. We can't use left or right with that because it depends on if I'm coming from the left side of the beam or the right. So with internal beam notation, we will always use positive and negative with our numbers, unlike reactions. So the first thing I'm going to need to do is find reactions. And so I'm going to look overall at my beam, draw this as close to possible. So we have BY, BX, because that's a pin. We have AY. I'm not concerned about C right now because we're just trying to find the reactions. And we have a uniform load, and we remember that the point load is just the area under the curve. And luckily, we don't have to integrate because we know that a rectangle is base times height. So we have 2 meters times 20 kilonewtons per meter equals 40 kilonewtons. And when we are looking at a rectangle, we know that it goes right through the centroid. 4 meters. So here's our free body diagram. We're just representing everything that we see here with point loads, sticks, whatever you want to call them on this side. So now we're going to have to use equilibrium. I can't spell today. I'm sorry. I'm trying to at least help you guys learn the system for solving these problems. Okay. So the first thing I'm going to do is sum forces in the x direction, which tells me that Bx equals 0. Do you have to find this? Yes, you do, because if I changed my loading conditions up here, Bx could actually have a value. So we need to make sure that we indicate Bx could exist, it just doesn't exist in this. And then because we have 2 y directions, solving y is not going to be helpful, so let's just sum the moments about B. And if we do that, I'm going to put a little dot there to remind me. Then I'm going to start at the left and move forwards. And we're going to use positive right-hand rule. And I'm letting you know we're summing moments about B, positive right-hand rule, everything equals 0. So we are going to have 40 kilonewtons times 5 meters minus AY times 4 meters. Okay, that's all of the forces that could create a moment, and the sum of those moments is 0. So we're going to get 4AY equals 40 kilonewtons times 5. And when we put that in our handy-dandy calculator, we have 40 times 5. And then we're going to divide it by 4, and we get that AY is 50 kilonewtons. We got a positive value, so our assumption of going up is a valid assumption. And I'm writing kind of big, so I'll zoom back out a little bit, okay? So we could start now, if I want to know the internals at C, I can cover up the left side, because remember, we can't just take a chunk out of the middle, we have to actually cover up everything to the left or to the right. And I notice that as long as I have AY, then I can solve for things at C. So now we're going to find internal at C. Okay, so I'm going to cover up the right side of the beam that I'm cutting off, and I'm going to look specifically at the left side, and I have to draw another free body diagram. Always, always, always. So this is going to be segment AC, everything that's on that. So as I draw my free body diagram, I have to start over with any uniform loads I might have, and because the whole thing is here, that whole rectangular load, we can know that that's 40 kilonewtons. We are going to start here with 50 kilonewtons, and that's all that we have for loads on that left side of the beam. So now we can assume positive beam behavior, and we can start calculating our internal forces. Okay, so we're going to use this free body diagram, not the one up there. I also like to go ahead and put what I have in terms of geometry because I don't want to have to think and look back. So it's nice to have everything on that free body diagram. So looking at N, we are going to solve forces in the X direction. Okay, I'm going to use to the right as positive. I'm going to go across my beam, and I have that normal force is 0. Do I have to include a normal force that's 0? Yes, because a normal force could exist. Okay, in this loading situation, it's 0. We could load it differently with some loads in the X direction and actually have a normal force. Let's sum our forces in the Y direction, left to right. We have minus 40 kilonewtons plus 50 kilonewtons minus V equals 0. Okay, so behaviorally, shear going down on the left is positive. However, when I come back over here for equilibrium, I have to use what I'm using for positive in terms of direction. So negative 40 plus 50 minus V, and I can work this out that V equals, we're just going to move that over, negative 40 kilonewtons plus 50 kilonewtons equals 10 kilonewtons. So my shear is 10 kilonewtons. With shear, I don't put an arrow up or down. I call it positive or negative because we are looking at, again, behavior. Okay? Behavior. If I'm coming from the left, down is positive. If I put the coming down here, then coming from the right, positive is up. I don't know what up or down means. Behavior is just positive or negative. Now let's sum our moments. And I like to kind of sum them about the cut I made. I just have a consistent method for setting up my problems. So we're going to sum moments about that cut. Okay, so I'm showing you summing moments about C, that's my cut. Right hand rule for positive, so we're going to work our way across. I have 40 kilonewtons. This time my moment arm is 3 meters because I'm just going to C. I'm not trying to find a reaction overall. I have a negative 50 kilonewtons times 2 meters. That's the distance to the cut. This is why you cannot use your overall free body diagram anymore. You have to use the free body diagram for the component of the question that you're trying to solve, okay? Plus, I have an internal moment at C. All of this equals 0, so my moment at C equals negative 40 times 3 plus 50 times 2. So let's plug this in, 43 times, 52 times. I'm going to add that, and we get that our internal moment at C is negative 20 kilonewton meters. Again, we are absolutely not going to put a direction on this. We are going to call it negative because it's behavior. A negative moment means our deformation of the beam is going to look something like a rainbow, okay? We're going to have compression on the bottom of that beam, tension on the top. If you're designing with things like concrete, it's very important to know where your tension and your compression, your pieces of your beam are so that you know where to put in that reinforcing steel. Let's go back up, recognizing this is negative, and let's look at our picture. If I'm pinned at B and I have a roller that's holding me in place at A, do you all see that if I put a force out here, it's like standing on a diving board, and this side is going to want to go down, okay? But because I have a Y component, because I have a Y component here, that can keep me from moving, then I can see that my beam is going to pop up something like that. That's what the behavior, that's what the deformation would end up looking like. And so that's why it's important to call it a positive or negative moment. Okay, over here, this would end up being a positive moment. This is a negative moment. So our negative 200 totally makes sense. Now, if you wanted, you could also go back and work this same problem. We could actually find the reaction at B and work towards the middle of the beam. So let's go back and do that. Let me find another sheet of paper here. Okay, so here we go. So when we looked overall, we found that AY was 50 kilonewtons, so we can go back to our overall, and we can go back to this, and we can sum forces in the Y direction, and we're going to have a negative 40 kilonewtons plus 50 kilonewtons plus BY equals 0. So we can find that BY equals negative 50 plus 40, BY equals negative 10 kilonewtons, BY equals 10 kilonewtons going down. Okay, can a reaction pull down? Yes, it can. If we want to look at our picture here, as this beam wants to follow its load pushing down, okay, it really kind of wants to go up. So B is having to pull down to keep it back in place. So yes, it makes sense that BY is going down. Now that we found BY, knowing that I want to know what C is, we could actually do segment BC. We could draw another free body diagram. We know that we have 10 kilonewtons down. I have 2 meters back to C. And internal, I could have a normal, a shear, and a bending moment. Oh, and you guys can't see that. Sorry about that. I have to use right-hand rule. Not right-hand rule. I apologize. Internal positive notation. So this time, when I sum forces in the x direction, I'm going to get a negative n equals 0. So my normal force is 0. Again, depending on how we loaded the beam, we could have a normal force. Let's now sum forces in the y direction, and I get positive y minus 10 kilonewtons equals 0. So my shear is 10 kilonewtons, positive by behavior. I can't show an arrow up. Let's go back here. Oh, we got positive. Sorry, positive behavior. I'm still learning how to make videos, so just bear with me. Again, we're not going to show up or down because here positive is down. Coming back from the right, positive is up. So we just show behavior, positive 10 kilonewtons. So now let's sum our moments about our cut. We know that in statics, it's super nice. Everything equals 0. So I'm going to start at my cut, and I can see that I have a negative moment at C. And these are at the cut, so there's no distance. Come over here, minus 10 kilonewtons times 2 meters. And all of this has to equal 0. So we have our force, and we have our distance. So we're going to find that the moment at C is negative 20 kilonewton meters. Again, we're going to keep it as a negative because that's telling us the behavior of the beam. Negative is once again telling us the deformation of the beam. Looks like a rainbow. We have compression and tension. And lo and behold, that's exactly what we got coming from left to right. So, like I always say, the absolute beauty of statics is that you should never have a wrong answer because you can check your solutions multiple ways. Okay, I'm going to turn this off and then do problem number 2.